In this video, we are going to look at sulfonate esters of alcohols as leaving groups, and then we are going to examine oxidation reactions of alcohols. Hydroxyl group of an alcohol is a poor leaving group. In the previous two videos, we have seen several methods to convert hydroxyl group into a good leaving group. Common to all those methods was that hydroxyl group was converted into an unstable reaction intermediate. So it was either protonation or conversion into some other oxonium ion that was a good leaving group. But in each case, it was an unstable reaction intermediate that immediately reacted in subsequent step. We, of course, have a need for stable leaving group that could be isolated so that alcohol derivative could be purified and then could be reacted with other nucleophiles. So that would expand range of reactions and transformations that are available to us. And one such leaving group is sulfonate ester. Sulfonate esters are prepared in a reaction of an alcohol with sulfonyl chloride in the presence of non-nucleophilic base such as pyridine. And you can see what is sulfonyl chloride. It's derivative of sulfuric acid, where one hydroxyl group of sulfuric acid is replaced by an alkyl group and the other one by chlorine atom. So highly reactive derivative of sulfuric acid. A pyridine is needed to neutralize hydrogen chloride that is evolved in the course of reaction. In general, reaction proceeds very well, cleanly, and in high yield. When we examine structure of sulfonic acids, sulfonic acid itself, so not the chloride but actual sulfonic acid, is strong acid. It's about as strong as sulfuric acid, and you can see that it has structure similar to that of sulfuric acid. It's just that one hydroxyl group of sulfuric acid has been replaced by a hydrocarbon substituent. It is a strong acid because resulting anion is very stable. So its conjugate base is weak base, it's stable base, and it's stabilized through electron delocalization or resonance. So three resonance structures are shown here. We have seen that sulfonyl chlorides are the reagents that are used to convert alcohols into sulfonate esters. There is actually a rather large number of different sulfonyl chlorides that are used for this purpose, and they have slightly different properties, slightly different reactivities, and some of them are the best for particular use. Here are the most commonly used sulfonyl chlorides. By far, the most commonly used is para-toluene sulfonyl chloride. It's known by its abbreviation as tosyl chloride, and its abbreviated formula is TSCl. So TS stands for tosyl, as you will see. Another one that is used a bit less commonly is methane sulfonyl chloride. Its abbreviation is mesyl chloride and abbreviated formula MsCl. And finally, one highly reactive sulfonyl chloride is trifluoromethane sulfonyl chloride or triphyl chloride, and abbreviation is TFCl. So the substituent that is placed on oxygen of the alcohol is, in the first case, in case of tosyl chloride, it's tosyl group. So this is the structure of tosyl group, para-toluene sulfonyl group, tosyl group, or TS. In case of methane sulfonyl chloride, substituent is mesyl group, or MS. And trifluoromethane sulfonyl chloride, substituent that is placed on alcohol oxygen is triphyl group, or TF. And here is the actual structure of alkyl sulfonate. So this would be an alkyl tosylate. As I said, this is by far the most commonly prepared, and that's because the starting material is actually solid. Para-toluene sulfonyl chloride is solid, so it's very easy to handle, even though it's corrosive and highly reactive, unstable towards moisture. Still, it's the easiest to handle of all of the sulfonyl chlorides. So this is by far the most commonly prepared. This would be alkyl mesylate, and finally alkyl triflate. Here are some examples of use of sulfonate esters as leaving groups. In the first case, we have reaction of a tosylate, tosylate that was obviously prepared from 1-butanol, and reaction with iodide anion. In this case, source of iodide anion would be potassium iodide. That's the most common inorganic salt that is used as a source of iodide anion. So reaction with potassium iodide would produce or result in formation of corresponding alkyl iodide, in this case 1-iodobutane. This is preferred method for formation of alkyl iodides or iodoalkanes compared to reaction of alcohols with hydrohalic acids. Reaction of alcohols with hydrohalic acids is not very clean, proceeds with number of side reactions, sometimes even with rearrangements, so yields are usually very poor and reaction is not very clean. This reaction results cleanly in formation of desired product in very high yield. So much better reaction. This is a typical SN2 reaction. There are no side reactions, no competition from rearrangements or other reactions, so this is definitely preferred method to carry out transformation like this. Another reaction is reaction with an alkoxide. We actually couldn't carry out this reaction because alkoxide is a base. We couldn't carry out this reaction by using one of the methods described previously. We couldn't use some unstable oxonium ion that is result from activation of hydroxyl group because we could not add hydroxide to such reaction mixture. But now, because tosylate in this case is stable compound, we can add, let's say, sodium methoxide, and product resulting ether would be formed cleanly and in high yield. Here is an actual two-step sequence starting with an alcohol. So we have 3-pentanol, reaction with tosyl chloride in pyridine results in formation of corresponding tosylate, and then reaction with a bromide salt like sodium bromide results in formation of 3-bromopentane. So typical two-step procedure starting with an alcohol. And this is how you would more commonly represent such a procedure. So let's say reaction of cyclohexanol, and in this case we are using triethyl chloride. So reaction with triethyl chloride in pyridine would give intermediate triflate, and then second step reaction with methyl thiolate, let's say sodium methyl thiolate, results in formation of corresponding thioether, or sulfide to use trivial name. Note that we have to use numbers 1 and 2 for the two steps. So number 1 for the first step, formation of triflate, and then number 2, reaction with thiolate. That's second step. If we didn't use numbers, that would mean that we are mixing all the reagents together, and that actually would not work. Such reaction would fail. We have to carry out first step, prepare and isolate tosylate, and then carry out second step. So that's what these two numbers mean. That we carry out first step, first reaction. Once that reaction is completed, then we carry out the second reaction. In the previous video, you have seen that an elimination of alcohol can be carried out under acidic conditions if we use an acid as a reagent, as a catalyst, or it could be carried out under neutral conditions if we use phosphorus oxychloride and pyridine as the reagent. An elimination of alcohol can also be carried out under basic conditions if we first convert alcohol into corresponding sulfonate ester and then carry out elimination with a base. So here is an example. 2,2-dimethyl cyclohexanol upon treatment with tosyl chloride in pyridine is converted to corresponding tosylate, and then reaction with a base, let's say sodium methoxide, results in elimination to give corresponding alkene, 3,3-dimethyl cyclohexene. And here is another example, 2-butanol, and again this is how we would typically represent such transformation. So we would write two steps above the reaction arrow. So first step, conversion to tosylate, and then second step, reaction with a base, sodium methoxide. Product is corresponding alkene, in this case 2-butene, and reaction mechanism, of course, as expected, is E2. Compare this with elimination under acidic conditions, and of course don't confuse the two. Make sure you don't confuse the reaction conditions. Note this reagent. This is paratoluene sulfonic acid. It's a very similar reagent, but this is actually an acid, and paratoluene sulfonic acid is sometimes used as a catalyst because it's soluble in organic solvents. So with heat, those are typical acidic conditions. Reaction mechanism would be E1 in this case, on this example of 3,3-dimethyl-2-butanol, and of course reaction would proceed with rearrangement and with all the other side reactions and problems associated with E1 reactions. On the other hand, reaction of the same alcohol, 3,3-dimethyl-2-butanol, first by treatment with tosyl chloride and pyridine would convert it to tosylate, and then reaction with sodium methoxide would be an E2 elimination, and reaction would proceed cleanly to give only one product, and that's 3,3-dimethyl-1-butene, without any rearrangements, without any side reactions. Elimination of alcohols will proceed under basic conditions also if an alcohol undergoes reaction under E1-Cb reaction conditions. That is the case if beta proton of the alcohol, so hydrogen on beta carbon, is acidic. So such hydrogen has to be activated by some electron withdrawing group, such as carbonyl group. Then this hydrogen could be deprotonated, and deprotonated hydrogen results in formation of carbanion. Then this carbanion will affect elimination of hydroxide. Even though hydroxide is a poor leaving group, the intermediate carbanion is extremely unstable. It cannot tolerate a negative charge on carbon. Actually, carbon is much stronger base than hydroxide. So this is actually a favored reaction, where free electron pair from carbon flows to form carbon-carbon pi bond and forces carbon-oxygen bond to break. And so that results in formation of actually more stable, weaker base, hydroxide anion. And so even though this is strong base, poor leaving group, compared to what we started with, this is favored reaction. And this is why E1-Cb mechanism works, because intermediate was carb anion, highly unstable carb anion. Now we are going to look at a different type of reactions of alcohols, at oxidation reactions of alcohols, and then at oxidation reactions in organic chemistry in general. Typical reagents. There are a number of reagents that are used in oxidation reactions of alcohols. Typical reagents are chromium reagents. So here are some. First one is solution of chromium trioxide in sulfuric acid. That one is called Jones reagent. Second one would be sodium dichromate, and then chromic acid in its various forms. Chromic acid itself is unstable, but in various solutions it is used. And finally, sometimes if you don't want to specify which chromium reagent is used, you'll simply say it's chromium 6, because common to all of these oxidizing reagents is that chromium has oxidation state of 6. And here is equilibrium between different chromium 6 species that may exist depending on concentration and pH of the solution. So under anhydrous conditions, chromium 6 is in form of chromium trioxide. In aqueous solution, it may be in form of chromic acid. At high pH, in basic solution, is in form of chromate anion, and in higher concentration, chromate anion dimerizes into dichromate anion. It is readily used, so these chromate reagents are readily react with alcohols, so they are used a lot in oxidation of alcohols. And here is an example of oxidation of primary alcohols. Primary alcohols are oxidized by chromium reagents, first to corresponding aldehydes, but reaction cannot stop here. So aldehydes are also highly reactive towards oxidation, so they are only reaction intermediates, and they are immediately further oxidized to corresponding carboxylic acids. So chromate oxidation of alcohols goes all the way to the corresponding carboxylic acid. Secondary alcohols are oxidized to corresponding carbonyl compounds, that means corresponding ketones. And finally, tertiary alcohols do not undergo oxidation reaction with chromate reagents. In these last two examples, oxidation of secondary alcohol and attempted oxidation of tertiary alcohol, reagent was Jones reagent. Solution of chromium trioxide in sulfuric acid. Reaction mechanism of chromate oxidation of alcohols involves initial formation of chromate ester intermediate. Here we can see it on an example of a primary alcohol. Reaction with unstable chromic acid, we assume that that is one of the species present in a solution. So reaction with chromic acid results in formation of chromic ester intermediate, that is highly reactive unstable intermediate, and it reacts in E2 elimination to give the corresponding carbonyl compound. So that is the actual oxidation step. So a base such as water picks up proton from the carbon attached to oxygen. That results in electron pair that carbon used to share with a proton. That electron pair now forms a carbon-oxygen pi bond and results in breaking of oxygen-chromium bond. So resulting species is carbonyl compound. In case of primary alcohol, that's an aldehyde, and in aqueous solution, an aldehyde is at equilibrium with its hydrate. So hydrate is this compound that has two hydroxyl groups on one carbon. So this is what we call geminal diol. And now this reaction could occur one more time. So one of these hydroxides can form another chromate ester, and since we still have proton on the carbon attached to hydroxyl group, then this elimination, E2 elimination, can occur one more time, and the final product is the corresponding carboxylic acid. So a reaction occurs twice. Reaction stoichiometry is 2 to 1. So one molecule of primary alcohol reacts with two molecules or two equivalents of chromate to give carboxylic acid as the final product. And intermediate is the corresponding aldehyde. In case of a secondary alcohol, the same mechanism operates, but after first E2 elimination, ketone is formed. Now, while ketones also form hydrates, that's where reaction stops. We have ketone-hydrate equilibrium. Equilibrium is towards ketone, and so when we isolate product, we isolate ketone. Corresponding hydrate cannot eliminate. It can form chromate ester, but since chromate ester is unstable, it will decompose back to hydrate. Elimination is not possible because there are no hydrogens, no protons on carbon that is attached to hydroxyl group, or hydroxyl groups in this case. And since elimination is not possible, reaction stops here. So in case of secondary alcohols, reaction occurs only once. Reaction stoichiometry is 1 to 1. So one equivalent of secondary alcohol reacts with one equivalent of chromate to give corresponding ketone as reaction product. And finally, that explains why tertiary alcohols are unreactive. While tertiary alcohol could form chromate ester, that ester is unstable and will decompose back to starting materials. There could be no reaction because in a tertiary alcohol, carbon attached to oxygen has no protons, has no hydrogens. For that reason, there is no elimination. E2 elimination is not possible, and so this unstable intermediate will simply decompose back to starting materials. As we have seen, primary alcohols with chromate reagents are oxidized all the way to carboxylic acids. Reaction cannot stop at aldehyde, at intermediate aldehyde, because under aqueous conditions, aldehydes are converted to hydrates, which are further oxidized. It would be advantageous if we could prepare aldehydes. Frequently, aldehydes are the desired reaction products. They are usually more valuable than corresponding carboxylic acids, and it would be advantageous if we had a method to prepare aldehydes by oxidation of alcohols. But this is not going to work if we have to carry out reaction in aqueous solution, because in aqueous solution we cannot avoid formation of hydrate, and then hydrate will be oxidized further. And we have to use aqueous solution because chromate oxidizing agents are water soluble, and we need suitable solvent for chromate oxidizing agent. So for that reason, special chromate oxidizing agent has been developed that is soluble in organic solvents. Such solvent is pyridinium chlorochromate. It's shown here, so its formula is shown here. its name, pyridinium chlorochromate, and it's best known by its abbreviation as PCC. Typical solvent for pyridinium chlorochromate is dichloromethane. So a reaction in dichloromethane, of course, can be carried out under anhydrous conditions in the absence of water. And in this case, since water is not present, hydrate does not form. So reaction stops at aldehyde. So oxidation of alcohols with pyridinium chlorochromate in dichloromethane results in formation of aldehydes cleanly and in very high yields. This is one of the best methods we have for formation of aldehydes. Now we are going to look at oxidation and reduction reactions in organic chemistry in general. You may recall from a general chemistry course that an oxidation and reduction reactions always accompany each other. Any oxidation reaction must be accompanied by reduction and any reduction by oxidation. So if one compound is oxidized, another one is reduced. And for that reason, sometimes these reactions are called redox reactions. And yet, in organic chemistry, we refer to particular reaction as oxidation reaction or reduction reaction. That's because organic chemistry is chemistry of carbon compounds, and we are looking at oxidation state of carbon atom. So we define oxidation and reduction reactions in organic chemistry with respect to carbon atom. So reactions in which oxidation state of carbon atom increases are defined as oxidation reactions. Obviously, something else will be reduced. And reactions in which oxidation state of carbon atom decreases are defined as reduction reactions. Oxidation state has to be calculated in each particular case, although we can draw some general rules about oxidation state of carbon atom corresponding to particular functional group or particular class of compounds. Still, they could vary a bit. So here are common classes of organic compounds and their most common oxidation states. So you can see how they are converted into each other and whether the corresponding reaction is oxidation or reduction. Of course, we have to define oxidation state, and oxidation state is defined as number of valence electrons of atom, in this case carbon, in ground state, minus number of assigned electrons. You may recall that this formula appears to be identical for formula for formal charge. But actually it's different because the way we assign electrons is different. In case of formal charge, we assigned electrons by assuming that each bond was covalent bond, and we split electrons evenly. So in case of each covalent bond, electrons were split evenly. Only in case of ionic bond or free electron pairs, those electrons were assigned to atom that they belong to. In case of calculation of oxidation state, for purpose of calculating oxidation state, electrons are assigned in such a way that each bond is assumed to be ionic. Even if we know that bond is covalent, we will treat it as if it were ionic, and we will assign all of the electrons from that bond to more electronegative atom. Only if the two atoms are identical, two atoms that form a bond are identical, or their electronegativities are approximately identical, then we will split electrons evenly. Otherwise, we assign all the electrons to more electronegative atom. Here are some examples of reduction and oxidation reactions in organic chemistry and how we determine whether they were reductions or oxidations. So in this first example, we have a reduction reaction, reduction of ketone to corresponding alcohol. A reduction is sodium borohydride reduction, something we'll cover later in the course. To determine whether reaction is reduction or oxidation, we only consider carbon atom that has undergone bond change. So two metal groups are unchanged in the course of reaction, we ignore them. We consider carbon that is part of the carbonyl group, carbon double bonded to oxygen. So when we consider that carbon atom, we can see that it forms two single bonds to two other carbon atoms. Since those are bonds to identical elements, to other carbons, one electron from each bond is assigned to that carbon. So a total of 2 electrons are assigned to carbon. Electrons from carbon-oxygen, double bond, are all assigned to oxygen because oxygen is more electronegative. In ground state, carbon has 4 valence electrons, so -2 assigned to carbon. Oxidation state of carbon is +2. After the reaction, carbon has 4 electrons assigned to it. 2 electrons we have seen before from 2 carbon-carbon single bonds, and then carbon is more electronegative than hydrogen. So both electrons from carbon-hydrogen bond are assigned to carbon. Still, carbon-oxygen bond, both electrons are assigned to oxygen. But total, 4 electrons are assigned to carbon. 2 from carbon-hydrogen bond and 1 from each carbon-hydrogen bond. So 4 valence electrons in ground state, minus 4 assigned electrons, 0. So oxidation state of carbon is 0. So oxidation state of carbon went from +2 to 0, so that this is a reduction reaction. In this second example, we have reverse oxidation of alcohol to carboxylic acid with chromate reagent. So when we consider carbon atom, in this case, carbon forms one bond to one other carbon. So one electron from that bond is assigned to carbon. And then there are 2 carbon-hydrogen bonds. Both electrons from each bond are assigned to carbon atom. That's a total of 4, plus 1 from carbon-carbon bond, 5. Of course, carbon-oxygen bond, those electrons belong to oxygen. So 4 valence electrons in ground state of carbon, minus 5 assigned electrons, that's minus 1. Oxidation state is minus 1. In the product, carbon forms one bond to other carbon, that's 1 electron. All other electrons are in carbon-oxygen bonds and they are assigned to oxygens. So only one single electron is assigned to carbon. So 4 valence electrons minus 1 assigned electron, that's +3. So oxidation state of carbon went from -1 to +3. So that's oxidation reaction. And here are some other examples. You can see another reduction. This is catalytic hydrogenation. We classify this reaction as reduction anyway. So oxidation state went from -1 to -2. Another oxidation reaction, oxidation of alcohol to ketone. So oxidation state of carbon changed from 0 to +2. Then we have dissolving metal reduction. So oxidation state of each carbon of the triple bond changed from 0 to -1. You can see in this case, these last two reductions, there were 2 carbons that underwent change, so you had to figure out oxidation state of each carbon. And here is an oxidation. You may not view this reaction as oxidation reaction. Again, we have double bond, so we have to consider each carbon of the double bond, and in this case it was an addition of halogen. So strictly speaking, this is still an oxidation reaction. If you wish, you can pause the video here and analyze each reaction in more detail and do calculation of oxidation state and analysis of your own. Now I will move on to another type of reaction that is neither oxidation nor reduction. While some reactions were classified as oxidation or reduction reactions, quite a few of organic reactions are neither oxidation nor reduction. And here is one example. Addition of hydrogen bromide to an alkene. So, as I already mentioned, when an alkene is starting material, or when 2 or more carbons undergo bond change in the course of reaction, we have to consider each carbon atom. And for reaction to be oxidation or reduction, all of those carbon atoms have to be either oxidized or reduced. If some are oxidized, some are reduced, then reaction is neither oxidation nor reduction, or if oxidation state does not change, then reaction is neither oxidation nor reduction. And so in this case, when we consider 2 carbons of the double bond, you can calculate oxidation state of each carbon atom, and you will find that each carbon of the double bond has oxidation state of -1. After addition of hydrogen bromide has been completed, now we have 2-bromobutane as the product. So we consider 2 carbons, carbon 2 that now carries bromine atom, and carbon 3 that now has another hydrogen attached to it. We can see that carbon 2 has now oxidation state of 0. So this carbon atom, carbon 2, went from -1 to 0. This carbon atom was oxidized. While carbon 3 has now oxidation state of -2. So carbon 3 underwent oxidation state change from -1 to -2. that carbon atom was reduced. So carbon atom 2 was oxidized, carbon atom 3 was reduced. So we cannot classify this reaction as either oxidation or reduction. So this is neither of the two. And so this is one of the numerous reactions in organic chemistry that is neither oxidation nor reduction. So only some of the reactions can be classified as oxidations or reductions, some are neither. And this completes this video in which we examined use of sulfonate esters in organic synthesis and then oxidation reactions of alcohols. Next, we are going to look into reactions of ethers.